Hello everyone. I hope I'm audible.
Yes, ma'am.
Oh, thank you. So this session is to help you solve problems or discuss your difficulties for the syllabus. So for this too, we are focusing on week 5 to week 8. Majorly, it contains few of the time response analysis, right? Like Routh Hurwitz stability criterion. And
Ma'am, can you solve some PYQs?
can you?
PYQs?
Oh, previous year questions.
Yes, ma'am.
Ah, okay. Yeah, will do. Okay, root locus and Nyquist, Bode, mostly this. There are lead lag compensators, but that won't come for your quiz. You don't have to prepare on this. The last week, I think it has. It will be there in week 8, last part or somewhere. So this we are focusing for the design assignment because designing a compensator within this time frame is not, it's a difficult job for MCQs and short answers. So we are leaving this like conceptual based questions might come. I'm saying the questions like design a compensator based on this, which is a very lengthy question, right? You might not encounter questions like that. You will not encounter questions like that. Okay, so focus on these concepts majorly, and there are some conceptual questions might be there. So prepare what is what, like adjust about it. Okay. Then out of this, we will start from route stability criterion, and a few things I want to refresh for you to strong in your concepts because since we are expecting MCQs, short answers, and comprehension questions, which also involves again a series of MCQ questions. We don't really rely on, most probably, we won't rely on questions straight away questions. We will be relying on conceptual based questions. So, if you understand the concepts, out of that, if you want ask any questions like relatable questions, to test your understanding about your concepts, this might be the priority for this exam in while comparing to the straight away solvable questions. Okay, I will explain it in further. So, in that aspect, so route habits, how you would have studied is how to find the stability of a system. There is a table, so you will write in terms of coefficients of the characteristics polynomial, and you will do all this multiplication and find whether the first column of the route Harvard's table is there is no sign change, then the system is stable. Otherwise, if there is a sign change,
Excuse me, ma'am.
yeah.
Ma'am, before route harvest, we have PID controllers.
Oh, okay. Okay, I missed it. Oh, sorry. So we have PID control. Uh, marks. I will come back. Okay. And starting from route, I will come back to PID.
Okay, ma'am.
So, if the first column of this route harvests, if there is no sign change, then the system is stable. If there is any sign change, then the system is unstable. That's how we studied about the route harvests. The few things more than this you want to focus is how the signs of coefficients of a characteristics polynomial or characteristic equation we used to call affects the stability of a system. For example, if I give a example like this, s square plus 3s plus 2 something, and I will give you another example, s square plus maybe s cube plus s square plus 2s plus 8. Okay, with this, with only this, without using Routh-Hurwitz, would you be able to tell whether the system is stable or not? Any idea?
Yes, ma'am. Yes, ma'am.
Why?
If in this equation, if sign is like means it is negative or positive,
Mm-hmm.
and we have the coefficient s3, s2, s and s0, all the powers we have, then we can say the system is stable. If
Mm-hmm.
one of the power will suppose s1 is not there and one sign is changed, then we can say that system is unstable.
Oh, exactly. Very nice. So all the coefficients are positive or there is no sign change. Maybe all the coefficients can be negative also. If there is a negative, then we will take minus as a common sign and nullify it, right? Because the right hand side is 0. So if all the coefficients are in same sign, then we can say, and also there is another subcategory, no coefficients are missing. In this category, we can say the system is stable, right? Any doubt in this? If some
Ma'am,
coefficients,
it
yeah,
means the second equation s cube plus s square plus 2s plus 8 is
uh,
equal to 0 is stable, right?
no, I'm coming to the point. Let me explain it completely. So all coefficients, if all the coefficients are positive and no coefficients are missing, the system is stable. That's what we learned so far. We are missing out one thing here, and the next thing is, so if some coefficients are missing, or if there is any sign change, then straight away we can say this system might be marginally stable or unstable based on the location of the roots, right? Marginally or unstable. This is a proven fact. We cannot change it. If there is any coefficient missing, the system might be marginally stable. If there is a sign change like positive and negative in the coefficients, then the system is straight away unstable. There is no ambiguity in that. But here, if you want to revisit this example, this statement that I wrote in a blue is a necessary conditions, but it is not sufficient. That's why where we forget to focus on it most of the time. So it is necessary. It says that if the coefficients are positive, the system is stable, but it need not explain that when the system is stable, all the coefficients must be positive. That's what the second example contradicts. If you write a Horwitz array for this equal to 0, 1, 2, we will write the first coefficient first, right? So x cube, s square, s power 1, s power 0. So this would be 1 and 2 in the first row and 1 and 8 in the second row, right? So how we will do Routh-Hurwitz? First we will multiply this 2 and then subtract it from this 2, right? So I'm multiplying 2 minus 1 into 8 divided by this coefficient, right? That is 1. This would give me minus 6 by 1. So here there will be minus 6. So this clearly states there is a sign change because these are positive, but this becomes negative. So clearly the system is unstable. So ultimately, please keep this in mind. Let me write it clearly. In order for the system to be stable, all the coefficients should be positive or should have same sign. This also implies this. Don't just stick to positive, right? Because if I write like this, is it same than this? Both are same, right? Because I can take this negative sign as common and take it this side and make it 0, right? So that's why I have written that bracket um, this also. So if it should have same sign, then in order for the system to be stable, all coefficients should be positive. But the reverse is not true. I cannot say I have all the coefficients are positive, so my system must be stable. Does not imply the system is stable. The system might be unstable in this case. I hope this is clear. If this is confusing, let me know. Okay. For a system to be stable, all the coefficients should be in the same sign, but the reverse does not imply the same. The converse is not always true. Okay. This is like a mathematical necessary and sufficient conditions. Please don't confuse with this. Prepare it properly in your mind. Take this as an example, then you can remember it for the exam. Somebody is putting anything in the chat. I couldn't see it. Okay, it's stable. Fine. Please interrupt me if I didn't see the chat box. I don't have another monitor now. Fine. We will solve few small examples, and we have very less time, so I want to cover most of the topics within that. If I couldn't cover, the next session we can do that. That's why we kept 2 sessions. Somebody couldn't join in the morning session, they can join in the evening. So this is like a Raut-Hurwitz. Same, s square, s power 1, s power 0. I'm writing coefficients. If someone struggles with how to write this coefficient and all, please let me know, okay? We are starting with the highest degree of the polynomial, so it is s power 4. That is the coefficient of s power 4 is 1. Then we will leave 1 and write the other same even. If we start with even, we will write even degree polynomials in the first row. If we start with odd, we will write all the odd polynomials in the first row. So I'm starting with even, so I'm taking s power 4's coefficient and s square's coefficient and s power 0's coefficient. Right, in the next row, I'm taking the one that I left in the first row, that is s cubes, s power 1's, and there is nothing other than this as a odd coefficients, odd degree coefficient, so I'm leaving it as 0. Now, first we have to multiply this minus multiply this divided by this element. Please don't confuse with this order. First, you have to do this always. Don't start with this minus this. That will give you a very wrong answer. You might think the system be unstable while it is stable. Okay, practice this before going for the exam. So this will give me 8 into 18 minus 1 into 16 divided by 8. So maybe, I don't know, 8 into 18. 144
144.
minus 16 divided by 8. 144 minus 16 divided by 8. 60. Okay. So I got 16 here. Again, I will do the same operation. 16 into 2. Oh, that will come here, right? 1 into 5 minus 0 into 1 divided by 1. I've written it properly, right? Okay. Fine. Then the next thing is this one. 8 into 5. 1 into 0. 8 into 5 minus 1 into 0 divided by 8.
5.
Right? So this will give me 5.
5.
This is 5. Again, I will follow the same thing. 16 into 16 minus 8 into 5 divided by 16. 16 into 16 minus 8 into 5 divided by 16. 13.5 around. You might write in fraction. When you do by hand, I'm using calculator. Again, this will give me 0, right? There is nothing here. So it is 0. And then if I do again, that this will give me 13.5 into 5 minus 0 divided by 13.5, then again 5, right? So if there is nothing here, then you will get the same thing, whatever it is here. So if I see this, there is no sign change in my first column. So the system I'm proposing, the system is stable. This can be told confidently from the Roth-Hurwitz. If you have this, you cannot just judge the coefficients, like judge the system stability with the coefficients only. But you can do Roth-Hurwitz always and prove that the system is stable, the coefficients are positive, there is no sign change in the first column, so the system is stable. That is the importance of Roth-Hurwitz. Why I taught this is, this gives the importance of the Roth-Hurwitz. If I see the coefficients or the nature of the coefficients of my system, and I cannot say that whether it is stable or not. But always when I do the Roth-Hurwitz, I will be able to tell the system is stable. Even though the coefficients are positive, it will tell here there will be a sign change or there is no sign change in Roth-Hurwitz. You don't have to worry about Roth. Okay, always do Roth and then tell that the system is stable or unstable. Okay, I will take one example that with the first row 0 or first element 0. So I'm taking some 1 by s power 5 plus s power 4 plus 2s cube plus 3s plus 5. So this is a transfer function. So I will take a characteristic equation that is a denominator of this transfer function. And please note, sometimes you will be given this g of s in the questions. If it is a twisted question, I will say 1 by s plus 2 and I have a negative feedback system and find the closed loop transfer function and then find the Roth-Hurwitz. You will, if the open loop system has been given in the question, you will always find the closed loop transfer function, then only you will do the Roth-Hurwitz, because closed loop system stability is what we are looking for. So if this is a system I have given g of s, then I have to find g of s divided by 1 plus g of s into h of s. Please be careful with this. Whether the question has straight away given the characteristic equation or it has given the open loop transfer function. If there is a open loop, then convert it to closed loop, then find the Roth-Hurwitz. So how do we do in this case? It will be 1 by s plus 2 divided by 1 plus 1 by s plus 2 into 1, right? So this will be 1 by s plus 3. So the transfer function should be this, not this. If you find a characteristic polynomial for this, then the whole will be wrong, right? Okay, so please be careful with this one. And for this question, we'll do the Roth-Hurwitz. S power 5, s power 4, s cube, s square, s power 1, s power 0. I'm taking odd polynomials 2, 5.
Excuse me.
Yeah.
So you are taking the open loop or closed loop? This
This is a closed loop.
this is closed loop. Okay.
Closed loop. Straight away I'm giving. Okay.
Okay.
Okay. I have made mistake here because there is a one coefficient is missing here, right? So should be s power 5, s cube, and s power 1. So it should be 3. Then s power 4, then s square is missing here. Is it really missing or I missed? Okay, sorry. I missed it. So it should be 2s cube plus 2s square plus 3s plus 5. Okay. So here also there is plus 2s cube is there. Okay. I will rewrite it because those who see this online, they might get confused. equal to 0. This is my characteristic equation. Then this becomes 1, 2, 3, 1, 2, 5. Right. So first thing I will do 1 into 2 minus 1 into 2 divided by 1. Then straight away it will become 0. Same coefficients in both rows, right? Then 1 into 3 minus 1 into 5 divided by 1. 3 minus 5, it will give me minus 2 here. So after finding this, I can say only the first coefficient of my row is 0, but it is not allowed because whenever you divide it, do the next operation, 0 into 2 minus 1 into minus 2 divided by 0. The divided by 0 is a problem, right? So we cannot allow the first element of the Routh-Hurwitz to be 0. So what we do is we are assuming the 0 to be the least smallest or smallest possible number, that is epsilon. So we are replacing this 0 with epsilon. We are saying it is not 0, it is nearly to 0, 0.000 something. So I'm replacing it with epsilon to avoid the divide by 0 problem. Okay. Now I am multiplying. Let me close it and open it. It's laggy. So I'm again doing this. So this will give me 2 epsilon minus of minus 2. This will be 2 divided by epsilon. This is 1. And again, if I do this epsilon into 5 minus 0 divided by epsilon, that will give me 5. Now, I'm doing this again. 2 epsilon plus 2 divided by epsilon into minus 2 minus 5 epsilon divided by 2 epsilon plus 2 divided by epsilon. So by solving this, 2 epsilon plus 2 minus 2 epsilon minus 5 epsilon square divided by epsilon. This epsilon will get cancelled when I take a common one, plus 2. So I will be left with minus 5 epsilon square plus 4 epsilon plus 4 divided by 2 epsilon plus 2. Again, this will be 0, the next thing. So if I multiply this, I would be left with 5 because there is no element here. So whatever it is there, that will come here. Okay. Now I have to see whether my system is stable or not. For that, I am taking the first column. So now I will come up with the equation if this is like this and what it would be, kind of. From in this equation, if I put epsilon equal to 0, if I replace again epsilon equal to 0, how it will be? That's how I want to measure it. S power 5, S power 4, S cube, S square, S power 1, S 0. First, by replacing 0 with epsilon, I have come up with the equation. Now I am replacing again epsilon with 0. This will give me 1, 1. This will become 0. And the next thing, 2 into 0 plus 2 divided by 0. Anything divided by 0 is infinity. In the next equation, if I put epsilon equal to 0 here, then 0, 0, 4 by 2, then it will become 2, right? Minus. Okay, I think I have made some mistake here.
Ma'am, there will be minus for epsilon, not minus 4 epsilon.
Minus 4 epsilon it will be, right? One minute. 2 epsilon by 2 minus 2 minus of 5 epsilon. That's what I got. So it will be minus 5 epsilon square minus 2 epsilon uh, plus 2 epsilon. These two will get cancelled divided by 2 epsilon. Oh, this is into. I'm sorry. This is into. That's not minus, right? So I cannot take common for this. So that's where I made mistake. When this is into. So it will be minus 4 epsilon minus 4 divided by epsilon minus 5 epsilon. Right. Now it will be same. So now it will become 4 epsilon minus 4 minus 5 epsilon divided by 2 epsilon plus 2. Okay. So there will be a minus as common. Minus 4 epsilon minus 4. Fine. So if I do, then if I put epsilon equal to 0, this will become minus 2 and this will become 5. Now, okay. When I replace epsilon with 0, I found there is a sign change. So the system is unstable. Okay. Fine. So similarly, when you do a Routh-Hurwitz, if all the rows become, or if for a particular characteristic equation, if all rows become 0, then you will replace it with the auxiliary equation that is happening in the next row, that is there in the next row.
Ma'am, can you show up a little bit?
Yeah. I will do another one. I'm looking for the example. That is an important method.
Ma'am, screen up.
Screen is not visible.
Yeah, not.
Okay. I will do this. Can I scroll?
Yeah, ma'am.
Fine. We will do quick example again. S power 5 plus 8 s power 4 plus 12 s cube plus 20 s square plus 16 s plus 16 divided equal to 0. Then this is little bigger one. 1, 8, 20, 16, 2, 12. Oh, 1, 8, 20, 16. That's right. 2, 12, 16. That's it, right? Right. Now I will do this operation. It will be 2 into 8, 16 minus 12. 4 by 2, 2. It will be 2, right? 16 minus 12. Okay.
Yes, ma'am, 2.
So instead of doing this, I'm replacing this with divided by 2. So this will become 1680. It will be easy for me to multiply. I'm just dividing the whole row by 2. So this will become 168 and 0. S power 5. Okay. Now 8 minus 6, 2 by 1, 2. And this will become 20 minus 8,
12, ma'am.
2 again. And 16 will be as it is.
Ma'am, second will be 12.
20 minus 8, 12. Okay, fine. 60. Right? I'm again dividing everything by 0. That will give me 168. So this will become 168. Okay, exactly like a above row, right? This 168 and 168. So anyway, this is going to be 0 when you multiply it, everything. So this gives me the entire row 0 problem. So how we will tackle this is, we will consider the above row when it is about to become 0, and we are going to consider that as an auxiliary equation. So it starts with s power 4 So the auxiliary equation will start like s power 4 because this row is 0. We will see the one above row and then we will start with that coefficient. So whatever it is starting. Maybe that coefficient, if it is s cube, we will start the auxiliary equation with x cube plus something. Okay. So 1 s power 4 plus 6s square, since it is a even row, plus 8 equal to 0. This is my auxiliary equation. We call this as auxiliary equation. There might be questions that will ask you to find the auxiliary equation from this kind of characteristic equation. So just remember what is auxiliary equation. Then we will differentiate it with respect to s. So if I consider this equation to be a, and the meaning I'm going to do is dA by ds and equate it to 0. So differentiating s power 4 will give me 4s cube plus 12s plus 8 will go to 0 equal to 0. So this will give me 4s cube plus 12s equal to 0. Taking s as common, 4s square plus 12 equal to 0. 1s will be equated to 0 already. So this gives me 4s square is equal to minus 12. S square is equal to minus 3. S will give me root 3j plus or minus root 3j, right? So this is the root of my auxiliary equation. Keep this in mind. We will use this later. What you are putting in chat box, I couldn't see. I'm talking about S power 4 after applying to make computation. Ah, yeah, that's right. That's right. Somebody asked, what is the difference between the two sentence? Are you referring to that it was positive, then it is stable, not positive? That doesn't imply stability refers to positive coefficient. Is it so, Ajay? Did you understand that?
Ma'am, means the both sentence is same. No?
Which one? The same, what I refer to now.
Yeah.
This one, right?
Yes. Yes.
No, no. Like the thing I want to explain is maybe I will reframe the sentence and tell you. Wait. For a stable system, the coefficient has to be positive or at same sign. But just because the coefficients are positive, that doesn't mean the system is stable. Is it clear now?
Yeah, ma'am. Understood. Understood.
Okay. Okay, please interrupt me. I couldn't see all the chat box here. Fine. Now, you keep this root, but take this auxiliary equation, differentiated auxiliary equation, and put it back here. 412. Replace
Ma'am,
it.
here only s is equals to 0. Only one s. It's not the s square.
1s is equal to 0 because we are taking 1s common outside, right? I can take only 1s because this has only 1s. If I take s square,
Okay.
then this
Okay.
will
Okay.
become 12 by
Understood.
s. Okay, fine. Now, we are replacing this with the coefficients of the differentiated auxiliary equation, dA by ds. So, what it will give me? 4s square plus 12s, right? So, 4, this will be replaced with 4s cube plus 12s, and then this will always be 0. There is nothing other than this, right? Oh, so this will become 412, and I'm just replacing divided by 4 because it is a multiplication of it. So I'm replacing it with 1, 3 and 0 for ease of multiplication. And this will become 6 minus 3 divided by 1, that is 3. Again 8 minus 0 divided by 1, 8, 0. So when I do 9 minus 8 divided by 3, 1 by 3, 0.
Ma'am,
Yeah,
we have to find the roots of auxiliary equation. No?
yeah, I have found it here.
Ma'am, you have find the equation is from dA by ds.
Okay. That's right. That's right. Sorry. Yeah, this is wrong. Yeah, you are right. So it is not for the auxiliary equation, it is for the main equation. I'm sorry. So for this main equation, we have to find it, right? So since this has a higher degree polynomial, I'm replacing s square is equal to x for ease of finding the roots. So this will become x square plus 6x plus 8 equal to 0. So then this will give me minus b. How can I 3 2 1 come? So minus b minus 6 plus or minus root of 6 square 36 minus 4ac 32 divided by 2a. So
Ma'am,
minus.
is x plus 2 and x plus 4.
Okay. This will give me minus 6 plus or minus 2 divided by 2. Then this will be minus 4 by 2, comma, minus 8 by 2, right? So it will be minus 2 minus 4, right? So my x is equal to minus 2, comma, minus 4, where x is s square, right? That's how we replace. So if s square is equal to minus 2, then s is equal to plus or minus root 2j. Again, this will become plus or minus 2j. Root 4 is 2j. Clear? So this is the roots of my auxiliary equation. Okay, let me complete this and come back here to discuss on that. So this will become 1 by 3, and the next row become, as these are 0, it will become 8. There is no serious sign change here. Everything is positive in this. So it is generally stable. But in this kind of problem, we have to look for the roots of the auxiliary equation here. So if the roots are repeated here, then the system is marginally stable or unstable. But here the roots are repeated, but like the roots are imaginary, but it is not repeated. So the system can be marginally stable, but it is not unstable, it's stable. Okay. So if I get 4 roots like s is equal to plus or minus 2j, again plus or minus root 2j, then the system is unstable because repeated roots at imaginary axis makes the system unstable. But there are imaginary roots, but it is non-repeating roots, right? So the system is marginally stable or stable. If the option only has stable or unstable, you could go with stable.
Excuse me, ma'am.
Yeah.
Okay, can you explain once again what is the role of this roots of the auxiliary equation in the stability?
Okay.
Once again.
So in general, how do we know the system stable? If the roots are negative, completely negative, then the system is stable. If even one roots lies in the right half of the explain are positive, then the system is unstable. So if the roots lies in the imaginary axis, that is in this here in this area, then the system will be marginally stable, right? But I'm saying if there are imaginary roots occurs at pairs, right? Imaginary roots cannot be the single roots. If there is a 2j, there will be minus 2j always. Imaginary roots occurs as a pair. So I'm saying if there is another pair occurs at the same location, then this will make the system unstable. So repeated imaginary roots will make the system unstable. If there is one pair of roots in an imaginary plane, then the system is marginally stable. If there are more than one repeated roots, then the system will become unstable. Clear?
Yeah, ma'am. Understood.
Okay.
If that means in the imaginary axis, if
Mm,
we found that the repeated roots
mm,
at the same location, then
mm.
it is unstable.
Unstable. Yeah.
Okay,
If only
got it.
one pair is present at one location, then the system is marginally stable. It may or may not in future, but for now it's marginally stable.
Okay, ma'am.
This
Got
is
it.
like
Thank
a
you.
disturbance because whenever you are lying there far from the axis, like imaginary axis j omega, the system become more stable. But when you reach here, you are in the verge of going to this side or this side. You don't know whether you will fall the right side or fall in the left side, right? So that's why we are calling the system as marginally stable. But if we keep two roots together in the same place, then it will definitely make more oscillation and push the system to the verge of instability. That's why we are saying it's unstable. Okay, I think I have covered most of the route stability problem. We will quickly look root locus, then we will come back to the frequency response. And just I'm telling whenever I'm remembering this, just in frequency response, look for how to find the phase margin, gain margin. We already solved some problem in the live session. So please revisit those recordings and find how to find the phase margin and gain margin. You know the formula for this, right? With this formula, how to get the information from the transfer function, how to put it here in this formula. Just try that. And the another important topic is how to find the transfer function from Bode plot. Bode plot to transfer function, Nyquist plot to transfer functions. This is another potential problem you would expect in your exam. And the next thing is how to find the phase margin and gain margin from Bode, phase margin and gain margin from Nyquist. We will do problems on this, just telling it right now, whenever I'm remembering it. Okay, fine. And in root locus, the problem can be of finding the breakaway point and what else? Angle of departure and finding the proper correct root locus diagram. These are some potential problem that you can expect. Right. We
Ma'am,
will do.
one question is there in the PYQ. I am solving it. The angle criterion.
Uh-huh.
That's a question.
Ah,
So can you take the concept of that also?
yeah, I'm taking to
Okay.
right. Okay. In general, you should know what is root locus. Root locus is the path taken by the system or a characteristic equation. More particularly, the characteristic equation when open loop gain A is varied from 0 to infinity. So if I have a transfer function like this, so I'm just changing k equal to 0 first and then go k equal to 1 up to infinity. So this will become 0 by s plus 1, 1 by s plus 1, 2 by s plus 1. So it's lagging here. Okay, up to infinity by s plus 1. So if I plot my transfer function for each and every value of this, and if I connect the dot together, then I call this as a root locus. Okay, locusing my roots. For every k, what are my roots of my system? That's what I'm saying a root locus. There are steps in root locus. I'm particularly looking for the angle criteria. So the first rule, please be aware of all these rules. The first rule is root locus are always symmetric about real axis. This can also be a true or false questions in your exams. So if you have a root locus like this, it won't be a proper root locus. It will always be symmetric about your real axis. This is a real axis, right? This is a imaginary axis. So whatever you have in your real axis, it can be like this, then it will be like this. So your root locus is symmetric about your real axis. That is rule number 1. Rule 2 is that each branch of the root locus origin from your open loop pole and ends in your open loop 0. Always roots locus starts from pole and ends to 0. This could be another potential true or false question. Root locus never starts from 0 and ends in poles. So remember this. It always starts with open loop poles and ends with open loop 0. That is rule 2. Rule 3 is that segments of real axis having an odd number of real axis open loop poles plus zeros to their right parts of the root locus. This mentions like if there is a pole, there is a 0 here. You know that we always mention x with pole. To represent pole, we use x as a symbol. To represent 0, we use 0 as a symbol, right? So if my system has this kind of placements, one root is in -2, one root is in -3, and the root is in +2, let's take. So I'm going to take a segment and check whether the segment will be in the root locus. For example, I'm taking this as, okay, I will start with that one. I'm taking this as P1, this as P2, this is P3, maybe this is P3, this is P4, this is P5. Okay, if I take points or segments like this and I'm checking whether it is in the root locus or not. This rule 3 says you have to see the right side to this segment, and if there is a combination of both poles and zeros which is in an odd number, then that segment is in the root locus. For example, if I take this point P1 right now, I'm taking right side to this P1. Are there any poles in the right side to this P1?
No.
No, ma'am.
So it won't be in your root locus. That's what it is saying, this rule 3. So I'm taking P2 and I'm looking to the right side direction of this P2. Are there any poles or zeros?
1, ma'am.
1. So it is odd number of pole, right? So it is in the root locus. So I can take this to be on the root locus. This segment is in the root locus. Then I'm looking for the next point P3. Again, when I look to the right side of the P3, there is 1 0. It doesn't matter whether it is poles or 0. It is a summation of poles and zeros, okay? Don't just look for poles, don't just look for zeros. Combination of poles and zeros. So to the right side of P3, there is 1 pole. So that will also be in the root locus segment. When I take P4, I'm looking right to that. There is 1 pole and 1 0. Combination of this gives me 2, that is even number. So this segment does not lies in the root locus, right? That segment won't come in the root locus. Then I'm taking P5. Again, when I count the poles and zeros right to the P5, 2 poles, 1 0, combination of this gives me 3. So this will be in the root locus. So if I draw a root locus diagram, I will see I'm mentioning this as poles and I have 1 0 here. So if I want to draw a root locus diagram of my system, so this is the root locus of my system, right? So this part won't come inside it. The red highlighted part won't come inside the root locus. That's what it is. Please remember the rule 3, combination of whatever segments you are considering, consider the right side of the segment, and if there is any odd number of combination of poles and 0, then that segment will lie in the root locus, otherwise not. Rule 4 is that this is very fascinating about root locus. So I am tracing the roots of my system, right? So I already told if my my root locus starts with open loop pole and ends in open loop zeros. And if there is any mismatch between these poles and zero, how the root locus will behave? That's what the real question is. So as I said by rule 2, this should be like this, right? The root locus are symmetrical about x-axis. But what this pole will do? There is no zero for it, right? So this will go to infinity. That's what the root locus suggests. So they are saying n minus m roots, where n is the number of poles and m is the number of zeros. This n minus m will go to infinity. That's what they are saying. If there is no zeros, particular number of zeros to go to from the open loop poles, then it will go to infinity. That's what this root locus says, and this has been given in terms of the equation like this, 2q plus 1, where q varies from 0 to n minus m. This is the overall formula to find how many roots will end up in infinity. Okay, this n minus m will tell you how many roots will end up in infinity, at what angle it is going to infinity. It can go to infinity like this at any angle, right? This is 30 degree if I take, this is 50, this is 90 degree something. So we have to find exactly at what angle it is reaching infinity. That will give by this formula, phi of a. That is rule 4. Rule 5 is the point of each and every rule can be a potential question. So please sit, find the rules for the root locus from your reference books and find it. 1 minute. Give me a minute. Okay. The rule 5 is the point of intersection of asymptotes. So that is also, that is has a formula, but summation of poles, we will see this while solving a problem. I couldn't explain it without a problem. Sum of poles divided by sum of zeros divided by n minus n. Okay, fine. Then rule 6 is breakaway breaking point, that we are going to see right now. Breakaway breaking. How to find breakaway breaking, that we will see right now. To do that, it will be dk by ds. And rule 7 is the angle of departure. So for what kind of problem this angle of departure will come, for what it won't come, that kind also we will see. Plus or minus 180 degree, 2q plus 1 plus 5, where q ranges from 0, 1, 2 until n minus n it will go. And rule 8 is point of intersection of root locus branches with imaginary axis can be determined by the Routh-Hurwitz criterion. That is rule 8. Point of intersection of root locus can be found by Routh-Hurwitz. Rule 8. Fine. Now we will see some example of what are all these rules and how to find each and everything with an example of system. I will let you know the angle criterion in between, okay? Okay, fine. So I'm taking an example. G of s equal to k by s into s square plus 4s plus 13. So this is my example. So the first rule, before doing the rule, there is a pre-processing this step, that is to locate your poles and zeros. Then only you can put it in the root locus diagram, right? Okay. Then only you can locate it in their root locus diagram. So the first step is to locate your zeros and poles. So this will give me s cube plus 4s square plus 13s equal to 0. Okay, instead of doing that, I will do straight away. Why should we include? So this will give me s equal to 0 and s square plus 4s plus 13 equal to 0. That is another. So this will give me minus 4 plus or minus root of b square minus 4ac, 4 into 13, 52 divided by 2a, that is 2, equal to 0. That will give me minus 4 plus or minus root of 9. Oh. Six divided by 2 equal to 0 minus 4 plus or minus. How can I split 32? 9 into 2 or 9 into 4, sir. Right? Divided by 2 minus 4 plus or minus 9 into 2, 3 into 2 by 2. So minus 4 by 2 plus or minus 3. It would be minus, right? So j would be there. Minus 2 plus or minus 3j is my root of the characteristic equation. So s is equal to 0 comma minus 2 plus or minus 3j is my root. Now the first step is to write the j omega. This is omega. So my roots are somewhere like this. This is minus 2. This is minus 3. Then it would be minus 2 plus or minus 3j.
Excuse me, ma'am.
Yeah.
The imaginary pole should be minus 2 plus minus 1.5 j, no?
How come? Because there is a 2 here, no? This 2 and this 2 will get
Oh.
connected.
Okay.
Okay. Good that you are being attentive. What I was doing. So we found the roots that is in 0. One root is in 0. Please, after finding this, don't leave this 0. Okay, because this is s cube. We already found this s is equal to 0. So the roots are s equal to 0, minus 2 plus or minus 3j. These are all the roots. There is any 0? No, right? The only k is there. There is no 0. So now the first rule is to trace your root locus. How to trace your root locus? We will take segments 0.1, 0.2, 0.3, and we will see if that lies in your root locus or not. So for this, I'm for P1 there is nothing right to that, so this will not lie in your root locus. So I'm just straight away discarding this point. And then for P1, there is one pole lies in the right of the root locus, so this will come inside the root locus. And when I check P2, this point, this segment, there are 3 poles. Now you have to consider this imaginary as 1, 2. 2 poles, individual poles. Even though it occurs in pairs, you have to consider that as a individual 2 poles. So this will be 1, 2, and again 3. So this will also odd. So this segment will also come inside the root locus. This entire negative real axis will be in your root locus here. So many people will consider this as a single root and won't consider this segment inside root locus. That is wrong. You have to consider individual poles, imaginary pairs also are individual poles. Okay, just to be clear, I'm rewriting it. Now all this entire negative real axis comes inside your root locus. Now you found this. The next step is to find the angle of asymptotes and how many poles will be there. Now you, by understanding, you know it starts with open loop poles and ends with open loop 0. But from your question, there are 3 poles or one individual real pole and 2 or 1 pole pairs, right? Totally you have 3 poles, but you don't have any 0. So your 0 is 0 here. There is no 0 in your system. So all this 3 will reach to infinity. That's what your understanding is. How can I explain it in using a mathematical equation to find the degree of it, right? That's why we are finding the angle of asymptotes. This asymptotes meaning it is going to infinity. So at what angle it is going to infinity, that's what we mean as angle of asymptotes. And also from where it is going, that means it is centroid. The center point from which it is going to infinity, that's what we are going to find as centroids. You know the difference between asymptotes, like asymptotes are lines that reaches to infinity from poles. So the angle of asymptotes we are finding. Then from which point? It can go from any point here, right? In the real axis, because everything is in the root locus. So we don't know from which particular point it is going to infinity. That point we are going to find using this centroid. So these are the two different formulas. To find the angle of asymptotes,
Ma'am, could you please explain how we take the zero as a zero or it is from assumption or something?
oh, okay. In your transfer function, the numerator is always called as 0, denominator is called as poles, right? So when you find the roots for this characteristic equation, we found 0 minus 2 plus or minus 3j. But there is no 0 here, right? There is no s term in the numerator. So your 0 is equal to 0. 0 of the transfer function equal to number 0. There is no zeros, meaning.
It's mean there is non-zero, not zero equals.
Non-zero. Yeah, there is no numerator term, particular s term in the numerator.
The zero equal to the origin.
Yeah, if you have some, no, you cannot say 0 to the origin, because the 0 should be origin, then you should have some s term here, right?
Yes, ma'am.
If there is a s plus 1, then you can say my 0 is at minus 1 location. But there is nothing like that, so we are saying no zeros. That's it. There is no location for any 0 here. Okay, I can say null for it. Okay, if it is confusing with the location, it's null 0. Okay, you cannot find a location for your numerator. Fine. Now we are finding the angle of asymptotes. For that, the formula is 180 degree into 2q plus 1 divided by n minus m, where q varies from 0, 1, 2 up to your n minus m, and n is the number of poles and m is the number of zeros. So here number of zeros, number of poles is equal to 3, because 0 minus 2 plus 3j minus 2 minus 3j, where m is equal to 0. There is no null 0 it is. So 3. So n minus m would give me 3 minus 0, 3, right? So I have to change my q from 0, 1, 2. The number should be 3. Okay, not until 3. Fine. Because you have to find the angles for the number of poles it is there, no? Only 3 poles are there. So it will become plus or minus 180, 2 into 0 when q equal to 0. Angle of asymptotes phi a equal to 2 into 0 plus 1 divided by 3. So it will be 180, 2 into 0, 0, 1 by 3, 180 by 3. This will become plus or minus 60. Fine. When q equal to 1, phi of a plus or minus 180, 2 into 1 plus 1 divided by 3, 2 plus 3, 3, 180 into 3 by 3 will get cancelled, plus or minus 180 degree. When q equal to 2, phi of a equal to plus or minus 180 into 2 into 2 plus 1 divided by 3 plus or minus 60 into 2 into 4, 6, 5, right? So this will give me plus or minus 30 degree. Sorry, 300 degree. And that's it, right? 3 I have found. So your angle of asymptotes will be plus or minus 60, plus or minus 180 degree, plus or minus 300 degrees. Fine. These are your angle of asymptotes. At these angles, the
Excuse
root
me.
locus, yeah.
How we get this plus and minus?
Oh, it is in the formula. Here it's. Sorry. Here.
Ma'am, earlier I thought that there will be not formula. I think this is the formula plus minus 180, 2q
This
plus
is
1
the,
divided.
yeah, in the formula itself, there is a plus minus, because your root locus aqueous, it is symmetric about your real axis, right? If your root locus goes to infinity in 60 degree, it will there is another symmetric mirror image goes to minus 60 degree, infinity via minus 60 degree. That's why there is a plus or minus.
Oh, I have a confusion in. I have seen somewhere that the formula is 180 plus 180 into 2q plus 1 divided by n minus 1.
Okay, and they might have missed plus or minus, but it doesn't matter, because If you remember that the root locus occurs as a symmetric, then you will automatically include that. If you don't
So
have used this
here
formula itself,
if we
yeah.
take here only 60, 180, and 300, we
Ah,
will get the same locus that we required.
see, if your one of your pole is going to infinity at 60 degree, let's take according
Hmm.
to the first asymptote. So then as this root locus is symmetric about real axis, there is something will go at minus 60 also, right?
Yeah, ma'am.
So then only your root locus will be symmetric about real axis. That's why we are including plus or minus. But even if you don't include plus or minus, you should be aware that you have this, if you have this.
Okay, ma'am. Got it.
But it's always good to include minus, plus or minus, because it makes sense, right? By formula. They would have intended to find only the degrees, not the directions. Then they might have ignored the plus or minus from wherever you found
Yeah,
that formula.
yeah, I think also, ma'am.
Ah,
Ma'am, in the chat box, some question is there.
okay, 1 minute, I'll see.
Hello, ma'am. Could you please
Yeah.
explain how can we find breakaway and breaking points?
Yeah,
Important.
I'm coming to that next. We are solving rule one by one.
Okay, ma'am.
We don't have mock papers, Sonali, because mock paper doesn't make any sense, right? You will that questions will not be repeated anyway. So we are just putting you in a river and let you swim through it. That's it. Okay, the centroid. As I explained before, we are finding the centroid from which point it is going to go to infinity. That centroid formula is sum of poles minus sum of zeros divided by n minus n, where sum of poles is first you take a pole minus 3 plus or minus 3j. I will write it like this. I have 0 minus 2 plus 3j minus 2 minus 3j. Excuse me, it is lagging a lot. Let me close it and open it. Okay, fine. Hmm. So my poles are 0, minus 2 plus 3j, minus 2 minus 3j. So sum of my poles would be sum of physically the location of poles. Then it will become 0, minus 2, minus 3j, minus 2 plus 3j. Summing all the poles minus summing all the zeros of my transfer function, that is null here, divided by number of poles. Then this is 1 pole, 2 pole, 3 pole. So that is 3 minus number of pole is again 0. Since there is null 0, the value of 0 is also 0. It is not location of 0, okay? Don't get confused with this. Then this will become minus 4 minus 0. This because this both will get cancelled when summing together by 3. So it will become minus 4 by 3. That is something around 1.3 minus 1.33. So this is where your root locus is going to go to infinity from this point in your root locus here. What happened to your bone? Somewhere from here, okay? If this is minus 2 plus or minus 3j, somewhere here from here minus 1.33, this is your centroid. From here it is going to infinity, your root locus. We'll see the complete image later. Just now we found all the important points. Then we found the asymptotes. The next point is to find the breakaway and breaking point. We found the centroid. So I just want to update the diagram for this step and then we will update then and then. So one of my pole is here. other poles are here. What I just found is minus 1.33. This is minus 2, minus 2, minus 2, sorry, my plus 3j plus minus 3j minus 2. So this will be minus 3 plus 3j minus 2 minus 3j. Fine. This is my pole diagram. And then from this, that is a centroid. That is again in black I'm representing. And it is going to go to infinity somehow like this. At a degree of 60 degree from here to here 60, here to here minus 60. Okay, this is first asymptote. The second asymptote that we found is minus 60 one asymptote, minus 180 another asymptote, right? So the another asymptote will go towards minus 180 like this. This from this pole, this 0 pole, the another asymptote is going to go at a degree of minus 180. The third asymptote, that is minus 300, sorry, plus or minus, right? These are plus or minus 300. I can equate it little to 300 minus 360, the whole rotation. Then I can say this is minus or plus 60 degree, right? Instead of plus or minus 300, I can say this is minus or plus 60 degree, because plus 300 would be 300 minus 360, it is minus 60. Minus 300 would be plus 60. So I'm taking it as minus or plus 60 degree. That is again the same asymptote. Minus or plus 60 degree. Third asymptote will also go in the same direction. Fine. So for all the three poles, we have found the asymptotes and we traced out the directions. The next step is to find so individually it will look like a very big thing, but if you break down, it will be easy. So for step 4, I'm going to find the breakaway and break-in point. There is an important thing in this breakaway and break-in point that I thought I need to do. One minute. Okay. This breakaway and break-in is important one here. How do we find this? The first thing is breakaway or break-in point either lie on real axis or exist as a complex conjugate pairs, like your poles. So since the breakaway and break-in is happening from poles, from open loop poles to open loop zeros, this will also happen like the same. Okay, you have another session. Okay, I can do it in the next session, but let me complete this one problem. You can find this. I am recording this session. You can leave and you can find this recorded last part, and then we can discuss rest of the problems in the next session. Those who want to leave, you can leave and revisit the recorded lectures. Okay, fine. So the breakaway or breaking point either lie on a real axis or exist as a complex conjugate pairs. If there is a root locus on a real axis between two poles, then there exists a breakaway point. If there is a root locus exists on a real axis, so between two poles, for example, if you have a real axis and there is two poles, then I'm saying there will be a breakaway point. This we call it as breakaway points in between two poles. if there is a root locus on a real axis between two zeros, for example, instead of this, I have two zeros, then I call this as a break-in point. What if it happens in between one pole and 1 0? How do we call this? Then this may be a breakaway or break-in. So please understand, if that point happens in between two poles, then we call that as a breakaway. If it happens in between two zeros, then we call it as break-in. But if it happens in between a combination of a pole and zero, then we don't really call it as breakaway or break-in. It can depend on your nature of your system. Okay. So for finding this breakaway and break-in, first we will take the characteristic equations and equate it to 0 in the form of B of S plus K into AS equal to 0. So your K term will be here, that A is your denominator where K is your numerator. You will rewrite your transfer function such that you keep K in the left hand side and rest of the things in your right hand side. And then you will do dk by dA equal to 0. And finding this will give you the roots of this will give you the breakaway and break-in point. So for this system, how can we find the same, or how can we do the same to find the breakaway and break-in point? So my system is K divided by S into S square plus 4S plus 13, which is easy to find in terms of this. So this is my open loop system, right? First, to find it, convert it into a closed loop system. G of S divided by 1 plus G of S into H of S. This will become K divided by S cube plus S 4S square plus 13S. That is my G of S again. I'm going to write a closed loop here. K divided by S cube plus 4S square plus 13S plus K again. This is my closed loop system. Always if you want to find a characteristic equation, it is for a closed loop system, right? That's why I'm finding closed loop system. Don't get confused here. So now I have S cube plus 4S square plus 13S plus K as my characteristic equation as I'm equating it to 0. I am going to rewrite in terms of K equal to B by minus B by AS, because keeping K in one side, left side, and equating L's to the right side. So this will give me K equal to minus S cube minus 4S square minus 13S. Now I am going to do dk by ds, where S is in the denominator. That's why I'm equating by ds. If I differentiate it, I will get minus 3s square minus 8s minus 13. Then I'm going to equate this to 0. So minus 3s square minus 8s minus 13 equal to 0. Taking minus as common, 3s square plus 8s plus 13 equal to 0. Finding roots of this will give me S is equal to minus 1.33 plus or minus J 1.6. Since I'm running out of time, I'm writing as it is. You can find the roots for it. So now we found the breakaway point, because this is happening in between two roots, two poles, right? So this I'm going to call it as breakaway point. Because we only have poles in my system, minus 1.33 is coming in between two pole pairs. So this is going to be a breakaway point for me, since it happens in between two poles. Now we have to check for the K whether it is positive and real or not. So to check for the K, for this we will resubstitute this S in the same characteristic equation, minus S cube minus 4S square minus 13S. Substitute S is equal to minus 1 by 33, place J 1.6 back to this equation. So if you do this, K equal to minus 1.33 plus J 1.6 cube minus 4 into minus 1.33 plus J 1.6 square minus 13 into minus 1.33 plus j 1.6 square, 1.6 power 1. So if you solve this, you can use calculator for this. You can simply calculate, put it in a complex conjugate, so complex mode, and then calculate this. And k is, when you find it, it won't be positive and real. If you solve this, you will find this k won't be positive and real. And also it can be shown that when s is equal to minus 1.33 minus j 1.6, the value of k is not equal to real and positive when you particularly substitute this formula. Because this is plus or minus, right? So when I have to substitute both plus and minus in the equation. When you substitute minus j 1.6, you will show that it is not real. Since the values for k when s is equal to this value are not real and positive, these points are not an actual breakaway or breaking points. The root locus has neither breakaway or not breaking point here. If this k equal to positive and real, then only we will consider this as a breakaway or break-in. So for this system, since it is not, no breakaway or no break-in points. So when you just repeating it, to find a breakaway or break-in, rewrite your equation so that you will have k in the left hand side and rest of the things in your right hand side. Then differentiate k with respect to s. You will find a root. Then resubstitute this root in your back to your equation. When you do this, your k should be positive and real, like positive values and real numbers. That should not be a imaginary or complex pairs. Then if it is positive and real, you have to consider that as a this point s is equal to this point as a breakaway or break-in with respect to where it is located. In between poles, then it is breakaway. If it is in between two zeros, it is break-in. If it is in between to one pole and 1 0, it can be breakaway or break-in. You don't need to name it, but something it is. But it's, on the other hand, if it is not positive and real, the system has neither breakaway nor break-in. Okay, if k is equal to positive, if s equal to some x value happens in between two poles, then this is breakaway. Which is breakaway? This s is breakaway. If s occurs between two zeros, then this can be called as break-in. If s is equal to x occurs between 1 0 and one pole, or one pole and 1 0, then this can be called as either breakaway or break-in. Either. Okay. On the other hand, if the top if statement, these are neither nested if loops. Okay. So this is the major master if loop. So else, if k equal to, sorry, not equal to positive and real, it should be not equal to positive or not equal to real value, then neither breakaway nor break-in. I think you are clear about this. Okay, just keep this in mind. Prepare this for some 1 or 2 marks.
Ma'am, if the k is positive and real, then the breakaway break-in point lies in the root locus. Is it necessary or?
Yeah, if it is based on where it is located. If it is between two zeros, it is breakaway. Two poles, it is break-in.
Ma'am, I'm asking that if the k is real and positive, then the break-in or breakaway point is in the root locus or
It
something.
will be in the root locus only.
Okay.
It will also always be in the root locus. It won't occur wherever the root locus is not there.
Okay, ma'am.
Okay. So the next thing is to find the angle of departure. So when we usually find the angle of departure is that, okay, I want to tell it with an example. Okay, fine. Couldn't find an example. First, the next step is to find the angle of departure. Departure angle is that you find the asymptotes. Is it really following the asymptotes or it is taking a different degrees? That's what the angle of departure is. This usually happens when you have a imaginary roots. For a real roots, your angle of departure will always be 180 degree around, even if you find it. So this will change when you have an imaginary root. So angle of departure plays a major role when your system has an imaginary pairs of poles. So the angle of departure, maybe I will call this something sigma A something 180 degree minus sum of angles of vector to the complex poles A from other poles. Just keep this. I will explain in detail what this sentence means. Plus sum of angles of vectors to the complex pole A from zeros. Okay, so for example, if you have roots like this in our system, the formula tells 180 degree minus sum of angles of vectors to the complex pole A from other poles. For example, if I am taking this as my complex pole, then I'm saying I want to add the sum of angles of complex pole A from other angles. I will add A degree and I will add B degree. That's what this says. And the next sum of poles are 0. If I have a 0 again in my system, maybe 2 zeros I have in my system, then I will say this particular thing will tell sum of angles of zeros C degree from other zeros D degrees. That is like C plus D. 180 minus A plus B plus C plus D. That's what this is telling. Clear what this formula tells you? Okay, fine. Now we will find the angle of departure for our system since we have a complex conjugate poles.
Ma'am.
I have yeah.
So only when there are complex conjugate poles, so we
Uh,
need to
find the
this.
angle of departure.
Otherwise, it is always minus 180.
Like otherwise, it doesn't mean you don't need, but even if you find, it will be 180 degree only.
There is one case I found it to be 0.
What? I didn't understand your question. What?
In earlier one of cases, I found it 0.
Oh, 0. Oh, okay. 0, 180 is same, no? For example, if you have a real roots like this, the angle from here would be minus 180 to this,
Okay.
0 to this. So both are 0 when it lies in the real axis, right?
Mhm.
So it doesn't matter. It won't make much difference when it comes to root locus signs.
And the denotion of angle, can you scroll a little bit down?
The denotion of
Angles. Can
ah
you scroll down, please?
ah
Yes, yes. The denotion of angle,
ah.
A degree, D degree, I think they are not so right.
Okay, you
In,
don't understand this how it is.
I'm getting that. I'm just
Ah
saying that denotion here,
ah.
A degree, D degree is not correct. I think so. If you can.
No, it's 90 degree. No, always conjugate poles occurs at a pair. So always the other pole for the conjugate complex pair will be 90 degree.
Okay.
That's why
No,
I'm putting right angle.
that might be correct, but see, at from zero, the
Uh-huh.
pole, the
Hmm.
pole zero, the denotion of angle A degree. Is it correct, ma'am? I want to recheck.
D degree. Okay, okay. The direction might be different. Just to explain what is the sum of vectors to complex poles from 0 that I mentioned it. I will explain in detail now. How to find that particular angle, inner angle or outer angle. That's what you are saying, right?
Yes, yes.
It should be like this. This is the degree, not this. Is it clear?
Yes, yes.
Okay, fine. So just I was focusing on explaining what it is, so I didn't bother it much. Okay, fine. Now, for our particular example, we'll see. I think all of your questions will be answered by this thing. So we have one pole that I'm naming it as P1 for ease of understanding. I'm going to name this P2. I'm going to name this P3. Since we are doing the first time, it will take little time to understand all these things. That's fine. So this is J3. This is going to be J minus 3. Sorry, minus 3J. This is minus 2. This is also minus 2. So this is my construction of pole pairs. Now the formula suggests it should be 180 minus sum of angles of A from poles plus sum of angle of A from zeros. So for us, for our particular problem, this won't be there because we have null zero. So we are going to concentrate only on the sum of angles from poles, right? So the first thing is, first I will calculate for P1. Oh, sorry, for P2, because this imaginary poles only we are bothered. P1 is always 0 or 180 degree. So for P2, I'm considering first. So I'm going to write. First, we need to draw vectors from all other poles to P2. How to draw vectors from all other poles to P2? I'm drawing here. This is one vector from P1. Yellow. Yellow is vector, right? And this is the other vector from P3. So for P2, I'm drawing two vectors. So the angle should be calculated like this. From P1, the angle is theta 1. From P2, the angle is theta 2. Right? First, we need to find what is, with respect to P2, what is theta 1 and what is theta 2. That's what we are going to find. Now you understood theta 1, theta 2 location, right? First, I'm locating one of the imaginary poles and I'm drawing vectors from other poles. If there is another pole here, I would have drawn from here also. So if there is no other pole, so I'm just leaving as it is. And I'm naming each and every angle with one name. From P1, it is theta 1. From P2, it is theta 2. Now we have to find what is theta 1 and theta 2. So my theta 1 would be 180 degree minus tan inverse of B by A, where B is my, if it is a complex, let me charge my laptop for a minute. Fine. Or your B by A is the imaginary, like complex. If it is A plus BJ, it would be tan inverse of the angle would be B by A, right? So that's how always we use this to find the G of J omega when it comes. So here for minus 3, minus 2 plus or minus 3J, this would be minus tan inverse of 3 by 2. So this will roughly give me 180 minus 3 by 2, 1.5. So okay, some value here. So this will give me 124 degrees around. That is my theta 1. Theta 2 would be 90 degree. That you know, you don't need to calculate. Even if you calculate the same 180 minus tan inverse of 1, again 90 will be there. So since it is a complex conjugate poles, this will always be 90 degree. So theta 2 is 90 degree. So the angle of departure, overall angle of departure, how do you find? For two poles, we have found it. For angle of departure of P2, we are considering for P2. So 180 minus overall summation of all the angles from the poles. So this will be 180 degree minus of 124 plus 90. So this will give me around minus 34 degrees. Okay. Now, angle of departure from P3, another complex conjugate poles. So how will I draw a vector for this? Repeating the same thing. I am going to draw a vector from P1 like this, and I am going to draw a vector from P2 like this. So I'm calling this as maybe same, but even since this is a complex conjugate pairs, this will again be an angle of same 34 degrees. Since root locus occurs as a symmetric about real axis, right? You don't need to find it again for P3. Even if you find it, this will be the method to find it, right? So this will again be 34 degrees. So your angle of departure for P2, that is minus 2 plus 3j would be 34 degrees, and minus 2 minus 3j also be 34 degrees. The last step, since we have imaginary poles, we have to find the crossing point on imaginary axis. Sometimes it may not cross the imaginary axis itself, because since we have poles here, and poles here, your root locus might cross your imaginary axis or might not. We don't know. That's what we are finding it right now. If it crosses, at what point it is crossing the imaginary axis? That's what this step will let you know. How to find it? Again, we will take the characteristic equation. Our characteristic equation is s cube. What else we have? S cube plus 4s square plus 13s plus k, right? S cube plus 4s square plus 13s plus k equal to 0. So now we are substituting s is equal to j omega. Substituting this will give me j omega cube 4j omega square plus 13j omega plus k equal to 0. This gives me minus j omega cube minus 4 omega square plus 13 j omega plus k equal to 0. First, we have to split this into two. One is equating real part equal to 0, imaginary part equal to 0. So, real part equal to 0, what are real parts here? 4 minus 4 omega square plus k equal to 0. This will give me k equal to 4 omega square, where 4 into some omega, we have to find the omega. Maybe from here we will know what is omega. This will give me equating imaginary parts minus omega cube plus 13 omega equal to 0. This will give me omega cube equal to 13 omega, omega square equal to 13, omega equal to root of 13 plus or minus root of 13. So this will give me omega equal to plus or minus 3.6 around. So when I substitute this omega here, 4 into plus or minus 3.6 the whole square. It will be 4 into 13, that is
It's already 13, ma'am. Omega
what?
square 13.
What per? It was not clear whatever you said.
Omega square value already given is 13.
Yeah. Just substitute as it is 13. So this will give me k equal to 42. So this is where it crosses. Omega represents the imaginary axis term, right? So I have a root locus here. So I have a breakaway or break-in point that I already found here, that is minus 1.33, and I have my if this is minus 3j plus 3j. Okay, this will confuse. Wait. If this is plus 3j, this is minus 3j, then I said that there is a point at 3.6 plus 3.6, it is going to cross. At minus 3.6, it is going to cross the imaginary axis. So the final root locus diagram would look something like this. From P2 at an angle of 34 degree, it is going to cross. This is the 34 degree. This is going to cross the imaginary axis and goes to infinity via 3.6. Similarly, since it is a symmetry, it is going to cross minus 3.6 at an angle of 34 degrees to infinity. There is another pole, right? So this is going to cross infinity at an angle of minus 180 degree, where this is your asymptotes. At this 60 degree of asymptotes, this both line will meet at infinity. Right? This line will meet at this asymptotes at infinity. That's what we found. So this is going to be 60 degree. This is going to be minus 60 degree. Clear?
Yes,
Where this is my center. This is how you find a root locus. For some problems that is simpler than this, which has only real poles, you don't need to find all this angle of departure and where it meets your imaginary axis. Everything will happen in your real axis. 2-3 rules will get to discard. So it will be much more simpler than this. I have taken a little more complex problem to explain all the steps. Okay, I'll post this in the drive link that we shared in our discourse forum, and you can look this. Also, you can look with the recorded session. We will again join by 3 o'clock, 3 to 4, right?
3 to 4, ma'am.
Yeah. Oh,
Ma'am,
Ah.
the pole in the center that is equal to 0,
uh-huh.
then where it will go?
Infinity towards minus
True.
180. That's what we found
Yes, yes.
from here.
Ma'am, can you take some body plot questions in the next session?
Yeah. Okay. We will take.
Body plot and microsystem.
Yeah, that's what we are going to cover.
Sir,
Cover.
ma'am, from plot we have to do the compute the calculation equation. That
Yeah,
question, ma'am.
that question we will take. Body to
Ma'am, this
transformation.
PDF will be in VKit folder on Drive.
What? BK folder. There is a question like that.
Okay.
We will solve. We will solve body to transfer function, Nyquist to transfer function.
Ma'am, is it possible in that we quiz 2 we will get answers like what kind that I mean there are part of questions, and in later part we have to find out that what kind of controller we need to add here, so that we can get, and also plot the relatable graph, or you may say question, equations.
Maybe we will give the plot in the option itself. We will ask you to find the proper plot. That might be a question. So we will give you a transfer function, and then we will ask what is a valid root locus diagram. So you have to do the steps. It will be easy based on your marks for that particular question. For example, if it is a 2-mark question, we will give you a very simple with 2 roots or 3 roots that is in the real axis and ask you to find the root locus. For example, if I give you a root locus like this, I have pole and I have a 0 here. Okay. So I will give you 2 root locus. I have a pole, I have a 0. So which one do you think as a valid root locus? Sorry.
The first one.
The first one. Yeah, this could be a potential problem because you should know the rule that root locus
I'm not
starts from.
asking like this question, ma'am. On the 1st April session, the one of our instructor had covered one problem in which after solving a lot of equation, you have to find out after all that for attaining this particular ESS, MP, or say anything, what kind of controller you will install over the plant, and thereafter define its equation, and thereafter plot its Bode plot, or maybe the root locus. These kind of long questions. Is it
No, no,
possible?
it's not possible. You won't expect, you won't get
That's
this kind of questions.
because
It
time.
takes lot of time, right?
Yes. Yeah, it may take around half an hour for a single question.
Yeah, yeah, you won't take that much question. There may be questions that in comprehension that you will be asked to solve some steps. For example, for this particular steady state error, find the controller gain KP. For with this KP, what is a different steady state error? This kind of connection questions may come, but we won't get to come from one concept to another. That kind of questions we won't ask. Don't no need to worry about it.
Okay, sure.
Okay. Fine. I will solve one more question that is in PPID somebody has asked. So we will do that and we will conclude it. Okay. For the system shown in figure below, what is the figure? R of S, that is some plus minus KP plus KDS 4 by S into S plus 2 Y of S. Okay, fine. Now, they're asking us to find the range of Kp, Kd such that the closed loop system is stable. So they have given the closed loop diagram, block diagram. They are asking us to find the closed loop transfer function first, and to that transfer function to be stable, what should be the value of Kp and Kd? That is the question here. How will you solve this? First, we have to find the closed loop transfer function, right? That should be the first step. So how do you find the closed loop transfer function? G of S is equal to 4 by S into S plus 2. Gc is equal to Kp plus Kds. So your overall transfer function will be G of S, Gc, G divided by 1 plus Gc into G into H, right? H is 1 here. So it will be 4 by S into S plus 2 into Kp plus Kds divided by 1 plus the whole term. Right? Now the both of the denominator will get cancelled. This is 4 into Kp plus Kds divided by S square plus 2S plus 4Kp plus 4Kds. So if I take a characteristic equation, this will be S square plus S terms are 2 plus 4Kd into S plus 4Kp equal to 0. So they are asking find the values of Kp, Kd so that this is stable. So we can use
Ma'am, can you
route
just
orbits.
up a little bit for
What?
1 second?
Okay.
Okay, ma'am, then.
Fine. Now we'll do the Routh-Hurwitz for this. So this will be S square S square S power 0. So S square is 1, 4, sorry, 4 kp. This is 2 plus 4 kd, 0. So when I multiply this, 2 plus 4 kd into 4 kp divided by 2 plus 4 kd. Okay, this will be 4 kp only, no? Since there is a 0. So for this system to be stable, all the first column should be stable. So this will give me 2 plus 4 kd should be greater than 0 and 4 kp should also be greater than 0. So understood that this they have asked range of that, they have not asked any particular value. So for this to be greater than 0, 4 kp greater than 0, this implies kp should be always greater than 0. That is a range of kp. For this to be stable, 2 plus 4 kd greater than 0, 4 kd greater than minus 2, kd should be greater than minus 2 by 4, kd should be greater than minus 0.5. So this is the range of conditions for the system to be stable. So always stability, look for the closed loop transfer function. Don't just start with s into s plus 2. That will let you do wrong things. These are some.
Ma'am,
Yeah.
I have a doubt that I have posted in the chat box. It is kind of similar question, but I can't solve it. Could you please explain that?
S square plus kp minus 3s plus 2 for absolute stability. Kp should be greater than 3. Find the range of kp to ensure relative stability as desired. What is s square? What is that? S cap equal to s minus 0.5?
Ma'am, it is for relative stability.
No, that is a condition or what? I
That
don't
is
know.
the condition.
That is a condition
Yes,
they
ma'am.
have given.
Yes, ma'am, in the question.
Okay. So the question is s square plus kp minus 3s whole s plus 2. For absolute stability, they have given the condition kp greater than 3. Find the range of kp to ensure relative stability. As desired, they have, that is s square or s cap, what it is?
It is S cap.
Is some, I'm taking s dash since it is a little confusing. Okay, that is s dash, some s variation. Okay, so the characteristic equation we know s square plus kp minus 3s. Maybe I will write like that. Plus 2 equal to 0. First, you have to apply the transformation from one plane to another plane. That is s is equal to s dash plus 0.5. I'm just rewriting this here in terms of s so that I can replace it in my original polynomial. Okay. This is the same equation written in different form. Now I am going to substitute this in my original characteristic polynomial. So wherever it is s, replace it with s dash plus 0.5. So this will give me s dash plus 0.5 the whole square plus kp minus 3 into s dash plus 0.5 plus 2 equal to 0. So this gives me s dash square plus 2 s dash 0.5. Oh, sorry, maybe 1 s dash. 2 into s dash into 0.5 is 1 s dash, right? S dash plus 0.25 plus multiplying this inside kp s dash minus let us keep as it is. Kp minus 3 into s dash plus 0.5 for now. I will expand it. So this will be Kp minus 3 into S dash plus 0.5 into Kp minus 3 plus 2 equal to 0. So now I'm grouping terms. First I'm grouping S dash square term. So for S dash square, there is only one term, that is S dash square. The coefficient is also 1. For S dash, there are this one. This is S dash. This is S dash. And that's it, right? So I'm taking S dash 1. And this is 1 plus Kp plus, minus 3. Minus 3. So another S dash term. Are there any other terms? 1 plus Kp minus 3. Minus 3. Okay. This will be multiplied with this. No, it won't be.
And then it will be half Kp plus 3 by 4.
Okay. So this will be Kp minus 2, right?
Yes.
And remaining are the constant terms, S dash power 0 terms. What are other constant terms? 0.25 plus 0.5 into Kp minus 3 plus 2. These are all the constant terms. So if I expand it, 0.25 plus 0.5 Kp minus 1.5 plus 2, this gives me 0.5 Kp
Is this
plus
Raoult
what?
it is Raoult Harvitz.
No, not Raoult-Hurwitz. No. Just I'm simplifying the term since it is a longer equation. Just trying to write in terms of this k equal to 0, not Raoult-Hurwitz. Okay. So the new characteristic equation will be S square 2. Just simplifying in terms of my own way of representing it. That's it. S dash Kp minus 2 S dash plus 0.5 Kp plus 0.75 equal to 0. This is my new characteristic equation with respect to S dash square. Now we have to apply the stability condition for S dash plane. What is the stability condition? For relative stability, all roots should lie in the left half of the S plane, should be less than 0, right? So here, when you, from your condition, this should be minus 0.5. So your real part of S dash should be minus 0.5. So here, for a second order system, for a general representation S dash square plus A1 S dash plus A0 equal to 0, it is stable if A1 equal to 0 and A0 equal to 0. You can use Raoult-Hurwitz for to understand this also. So we are making all these coefficients to be greater than 0. You can use Raoult-Hurwitz for, since it is a second order equation, I am using like this. 0, Kp should be greater than 2. And for 0.5 Kp plus 0.75 should be greater than 0. So this gives me 0.5 Kp greater than minus 0.75. Kp greater than minus 0.75 by 0.5. And 0.5, right? So out of these two, which one is the least? This is the least. So the least possible or the good cap is that Kp should be greater than minus 1.5 for relative stability.
Okay, ma'am.
Okay.
Ma'am,
running out.
here you don't find the overlapping.
No need, since it has a real numbers. You don't need to do that, I think.
Okay, so if the KP greater than 2 is not satisfied when it is KP greater than minus 1.5,
Uh,
thereafter also it may satisfy the equation.
you are telling if KP, this is minus 1.5, this is 2. You are saying this region.
Yes, yes, ma'am.
In that case, 2 should be the border. It should be at least, okay, yeah, you are right. Like,
That's what I'm
KP
saying.
should be
The overlap.
at least greater than 2.
Yeah, yes, yes, ma'am.
That is right. Yeah, this is. But if you want to satisfy both relative stability and absolute stability, from your question, where it goes. Okay, sometimes it will be like this. There is a glitch. Okay. In your question, this is KP equal to greater than 3, right? So for it to satisfy both absolute and relative, the KP should be minimum greater than 3. If it only satisfies relative stability, KP should be minimum greater than 2. Okay, I'm concluding right now. We are already more than 1 hour, it's 2 hours now. We will meet you again in the afternoon. Most probably I will come, or Jada will take. I will pass that requirement, like Bode to transfer function, Nyquist to transfer function, if he takes. Okay, see you.
Okay, ma'am.
Ma'am, please upload this PDF.
I will upload it right now. The submission, the drive link.
Means in week 8 folder. Hello?
Thank you. I will upload it.
Thank you, ma'am.
Means, ma'am, in which week folder?
Not
Oh,
weak folder, it's in the drive link of.
drive link in the discourse forum. We have
Yeah,
uploaded the
means
drive
in
link.
the drive link there is 12 folders of week.
Oh, I will create a new folder like a revision for quiz 2, and then I
Okay,
will upload
okay,
it.
okay, okay.
Okay. Thank you.
Thank you, ma'am. Have a nice day.